My name is Daniel Archambault, and I'm presenting on essentially what I did over my summer vacation. So as everybody knows, a lot of their summer plans were interrupted by COVID. And so essentially I spent most of the summer immersing myself in an important problem, which is trying to make sense of simulations of contact tracing networks. Now, it's important to note that a good portion of this work was not only done by myself, but I was working with Çağatay Türkay at the University of Warwick. A little bit later on about how we met and how we were working together on this. So many of you probably know from my previous Why It Matters talk that my area of expertise has been network visualization, in particular social network visualization, where what you're trying to do is you're trying to make sense of online communication networks. And so I've written many approaches. One of the more recent ones shown here, which is DynNoSlice, have been written for this purpose and to make sense of how these networks and communication online evolves over time. Now, one of the things that you can immediately notice is online communication probably has some connection with contact tracing. So instead of individuals sending messages or posting on Twitter, et cetera, you could have a situation where an individual is infected with COVID-19, and because of a period of contacts, there's a transmission or an edge that infects someone else. And so I thought that a lot of my previous research could be repurposed for this. And so I did what anyone would do. So I contacted Min Chen. Min Chen is now a professor at the University of Oxford. For the longest time, he was a professor at Swansea University, and is probably one of the main reasons why I decided to come to Swansea in 2013. Min was heavily involved in something called RAMP, and I'll explain that in a second. So what is RAMP and what is the SCRC? Well, what RAMP is the Rapid Assistance in Modeling the Pandemic. It was run by it is run by the Royal Society, and it's the Royal Society's response to COVID-19. And SCRC is what they call a constituent group of RAMP. So the SCRC, or the Scottish COVID-19 Response Consortium, its aim is to advise the British government on policies with respect to exiting things like lockdown and that sort of thing. It consists of 6 modeling teams, one of them being contact tracing. And the visualization response was led by Min Chen of Oxford. Over 20 visualization researchers are participating in this consortium. And it was interesting because about once every 2 weeks, I was participating in Zoom calls of 100 people from various disciplines, trying to figure out how to respond and contribute visualization technology to the COVID-19 response. So in the end, we ended up working fairly closely with, and we continue to work closely with, some epidemiologists. Sibylle Mohr, she works at the University of Glasgow. She's a postdoc there. Originally, her postdoc was on diseases between livestock, things like hoof and mouth disease and that sort of stuff. And a lot of her simulation work is now being ported over to simulating and understanding COVID-19. And Professor Louise Matthews is also up at the University of Glasgow. She's originally a mathematician, and she has since applied her work to epidemiology before COVID and now with COVID. It's always important to collaborate with epidemiologists, and it's important to make things clear. I didn't know anything at all about epidemiology or any of these things before May, and it's always important to find people that know more about this subject than you do, so that you're sure that you're working off of the proper science. What I contributed in this project was mostly the visual interfaces, and now that I'm contributing visual interfaces for this problem, I'm starting to understand and also contribute a bit to the modeling side. Okay, so the first thing that I had to learn, this is pretty boring for your average epidemiologist, but for your average person like me who knew nothing about this area earlier on in the summer, you have to understand a little bit about disease progression and modeling. So you have something called an SCRC simulation, and this is a susceptible, exposed, infected, recovered simulation. There's two ways you can do this. The first way is you can have a series of a whole bunch of differential equations. People move from the susceptible to the exposed bin based on certain probability. That's when they get exposed to the disease. And then they can move from the exposed to the infected bin based on certain probabilities. That means they actually have and are affected by the disease. And then they can move to the recovered bin with a certain probability. So you can do this as a series of differential equations, or you can also do this as networks. And over the summers, I was doing networks, but I'm starting to get involved in the first thing that I was talking about. But if you do it with networks, or if you do it with a series of differential equations, you always have this, this map that actually describes how the disease progresses through the population. So remember, I said previously that it was called SCRC, susceptible, exposed, infected, and then recovered. COVID's a little bit more complicated than that. And this is the epidemiology that was published by the Irish Epidemiological Society. And it has been used pretty much by the SCRC as well. So over on the left-hand side, you have susceptible. Susceptible is your population that's susceptible to the disease. With COVID, it's a lot of people. And then a certain portion of that population gets exposed to the virus. Here is where things get complicated. So you have one pathway. So in the media, you hear the terms asymptomatic and pre-symptomatic. A lot of people seem to be using these interchangeably. They are very, very different. And this branch actually describes their primary difference. So if you're asymptomatic, you transition here. So the person, this is sort of like a flow diagram. The person moves through this flow diagram, susceptible to exposed. Then if you're asymptomatic, you transition up to this node down here. And then eventually you're going to recover. So an asymptomatic person will never show symptoms and will never get the disease, but they could spread it in the case of COVID-19. So when you're in this state here, you have the potential to spread the disease even though you aren't showing any symptoms. And when you're in the recovered state, essentially you're no longer infectious. Okay, so then you have exposed. If you're unlucky, you go to a pre-symptomatic state. In a pre-symptomatic state, you're not showing symptoms at all, okay? But you're still infectious. And because you're labeled as pre-symptomatic, you'll automatically transition into a symptomatic state where you actually begin to present symptoms of the disease. So that would be your fever, that would be your cough, that would be your loss of taste or smell. Okay, from here, you have essentially 3 other transitions that are possible. The first is you can recover. So you self-isolate and you beat the disease on your own. You could be hospitalized, and from hospitalization, you could either go to recovery or you could unfortunately die. And likewise, from a symptomatic thing, you could unfortunately die as well. And so in either the graph-based model or the differential equation-based model, you have individuals, and these individuals, as the simulation progresses, moves through these nodes, and you, at each individual time point, you can determine what portion of your population in this simulation is each of these categories. Okay, so we were doing a graph-based model because I visualize networks. So the individuals are essentially in a stochastic network-based model with what they call a compartmental structure, and the compartmental structure is what I just explained. So underlying all of this, you have something called a temporal network, which I'm going to give you a little bit of an idea of what that is first. And that's essentially the population going about their daily lives. Okay, so people live and they make contact with other people over the course of the day. And then what we end up doing is we end up simulating a spread of COVID-19 across this population that's undergoing contacts. So what do we mean by this? So we start with a very, very large network. So this very, very large network models people, and it models their contact. So this image here is actually has nothing to do with COVID. It's just for illustrative purposes. So you have this network of about 1 million nodes. Each of those nodes is a simulated individual. An edge is a tie that links a person A to a person B. So a mother picks up her child at school. A father visits his parents at an old people's home or something like that. This tie has a time associated with it. And so, you know, that could be at 4 o'clock on Thursday or something like that. Okay, so you have this long list of edges of people just meeting and coming together and partying, et cetera, et cetera. Okay. And then on top of this million edge network, you infect certain people with COVID-19. And then based on a simulated government policy, the disease begins to spread. So you'll have all of these different sets of trees where the disease will begin to spread to other individuals. And this is known as an infection map. And the infection map will tell us in the simulation when an individual is infected, by whom, and it will give these long chains, well, these trees to basically tell us in the simulation how the disease spread under these parameters. And although we start with a network of millions to tens of millions of nodes and edges, we end up with a map of several thousand. So these types of simulations are actually good for smaller populations, probably like on the city size. So if you're looking at simulations on a country or county size, much larger populations, you'd use the differential equation model. I'm starting to get involved in some of that, but this is really important. So we thought this was going to be important around now, but as we're still in the middle of lockdowns or regional lockdowns, it's becoming less important just basically because COVID's so prevalent in the population. But as we have more local outbreaks and it becomes necessary to contain them, this sort of technology and simulation becomes quite important. Okay, so you have your infection map, and this is sort of what it looks like as an output. So you have a bunch of simulated individuals. You have a certain time. In this case, we had a time resolution of about a half day. And then you have an edge, and then what this would mean is individual 13 was infected at time 0 and passed the disease on to individual 15 at time 5. Likewise, individual 15 at time 5 will pass it to all of these individuals at these times. Okay, so now you have this data and we want to look at it. One way we can look at it is we can look at the progression of the graph under different policies at a macroscopic level. So as we mentioned before, we have this way to model the states. So E is your exposed, and we have symptomatic and severely symptomatic here, all of the states that we had on the graph a few slides back. And what we can do is we can restart this policy and run it under different conditions. So you have your network. The network is the contacts. Contacts are going to happen in a specific order based on that network. And then you apply the disease in the policy. So in this case, we tell essentially contacts, all contacts of somebody who tests positive for the disease to self-isolate for 14 days. Another policy could be isolate all contacts until tested. If positive, isolate for Y days. If negative, release. And what you can do is, based on these simulated policies, you can decide if certain edges are going to infect or not. And at an aggregate level, you can look at the number of people that lie in each of these bins. And so that's good for a macroscopic view, but what we might want to do is we might want to look at the individual infection maps and for trends in how they work. So the very first thing you can do is you can do something called time flattening. And what time flattening is you take all of time and you flatten it into a plane. And then what you do is you color the nodes based on when they occurred in time. So these dark nodes here occurred earlier in the simulation, and the lighter nodes occurred later in the simulation. So one of the good things about time flattening is you have a better idea of how the disease is progressing in terms of details. Part of the issue here is looking at particular times during the progression of the disease could be more difficult. You can also use these time flattening views with statistics to take a look at how some of the disease progression works over time. So going back to DynNoSlice, where does this fit in? Well, we have a temporal network. What's a temporal network? A temporal network is where nodes and edges have individual points in time. So a node and edge has its own timestamp. This originally was quite important for social media analysis. And if you look at our infection maps, we have the exact same thing. And so it seems that DynNoSlice is actually in a very good position to look at these contact tracing networks. So if you look at previous network visualization approaches, they didn't work that way. Essentially what they did was they sampled the time dimension. So they took several slices of the time dimension and took all of the events and projected the events down onto the nearest slice. Now, why would anyone do this? Well, if you look at dynamic graph drawing algorithms, if you do this, it's very easy to take your favorite algorithm for drawing static graphs, graphs that don't evolve over time, and use this structure to draw dynamic graphs. Also, it has a huge advantage that by doing this projection, you get rid of information and you speed up the performance of your algorithm. But the main issue is that you will lose temporal resolution. So because you've done this projection, you're going to lose some temporal information, and that can affect your layout. So what DynNoSlice is we no longer do any of this sampling. What we do is we consider all of the events, so all of the edges and nodes, at their true time coordinates. So there's no loss in temporal resolution. However, we need to optimize this thing over the entire space-time cube. And these contact tracing networks look more like this. So some of the cost-benefit analysis for contact tracing networks, we might get more benefit from these more event-based approaches, which I invented a year ago for drawing. And here we go. So now, here's the progression of a large COVID-19 infection simulation on top of a contact graph. And this is the infection map. And as you can see with this policy, it was, first of all, earlier on in government policy, there's a lot of connected components. And what these connected components are people coming back from overseas. And essentially, because there's low levels of restriction, the graph is getting quite dense very, very quick. So this will provide a little bit of an overview of a simulation of earlier on in the COVID-19 pandemic pre-lockdown. And then subsequently, what we were able to do is look at disease progression in terms of this. So in this network, white nodes are asymptomatic nodes, green ones are recovered, red are symptomatic, and black ones unfortunately have died. And we can see how the disease progression and the state of each of the individuals progresses over time. And this is the 30 largest components of a simulation. So another way to tackle this has been to look at disease progressions according to geography. So at the same time, just by accident, I had a project with some people in Germany, and this was on infections in hospitals. So we were looking at how antibiotic-resistant bacteria spreads through hospital wards. We won an honorable mention at IEEE Viz, which is the top conference for visualization this year for this work. This work is currently being trialed in Germany in response to the COVID-19 pandemic. And we are looking at integrating this with things like DynNoSlice for the SCRC work. So what are the next steps? One of the really good things about our current model is it's very, very realistic. But one of the unfortunate things is each time you run the simulator, you get a different answer. And the reason for this is there's a fair bit of randomness in the simulation. It turns out that a lot of our policy people want to see, if I applied this policy to this infection map, what would be the difference? And it's kind of hard to do that with all of the random seeds. So what our solution is going to be, you take the COVID simulation, you run it without restrictions. So this would be the worst case scenario. And then what you do, instead of rerunning the simulator, you apply the rules to that map because you have all of the information. You can look back in time. And then what you can do is you can gray out or prune trees that essentially would have been stopped by people complying with the policy. So we're currently doing this for several government policies, and also we're looking at app usage, and we're trying to figure out how effective the app would be based on uptake levels. Okay, another area that we're just starting is visualization of estimations of parameter space. Remember way back, I talked about there's two ways to do this. There's either the way to do it with networks, which was basically the entire version of this talk. And then there was a way to do it with differential equations where you model these individuals progressing through the graph. In this second method, one of the main problems is running one of those simulations, although you can run it on something like the size of England or the size of Wales, which you can't do with the network model. It takes about a half day to a day to get an answer. And when the government is asking 25 questions, it's very hard to run 25 simulations because it could take close to a month. And so we're thinking of ways of visualizing parameter space and estimations of the results so that you can run 4 or 5 really fine-tuned simulations to get accurate answers. And then you can use machine learning and stochastic methods in order to predict the results roughly for the other areas. And this is much faster. And then you can use this parameter space map in order to do closer runs for the interesting areas of it. So I have to also thank a whole bunch of funders. So in the past few months, I've been part of, 2.5 successful grants. So most of the work that I'm talking about here are these 2 grants here. And the final one down here is a consortium that's being led by Min Chen. It's not accepted yet, but the last I heard is we had 3 very positive reviews. So we're hoping and praying that one gets in. I also need to thank VizTIG and the Turing Institute. Part of the reason why Chitai and myself had started working together was because of this group. And they've also provided a very good platform for me to talk to important people and collaborators across the UK, both in academia and in government. And with that, I know I'm way over time, but I'll stop there and take questions. Thank you.
Okay, you're on mute, so if you want to ask a question, just remember to unmute yourselves.
I have a question.
Hey, Arno.
But if you, I mean, my guess is that in that sort of there are quite a few parameter choices that you have to make where it's probably not that clear what the sort of correct values are. And since you mentioned that that's your randomness already has a huge impact on what happens. Do you know anything about stability for parameter values?
So there's 2 ways you can handle this. There's the most realistic way is essentially you do many runs of the emulator and look at trends across that. And then you can start running statistics and figuring out bounds of each of the transitions and that sort of thing. So there's that way, which you can definitely do, the statistical way. And then on top of it, you can also essentially run things based on a particular instance. That's a little bit less realistic, but at that time you factor out the randomness. If you're talking about tuning parameters, there's also 2 ways for that. The first way is you rely on the knowledge of your experts, and they're the ones that basically tell you exactly what ranges we should be doing for certain scenarios. That is one way of doing it. The other way is more similar to what I was talking about before, and we've just started doing this. So you get the experts to tell you what the parameters are for important runs, and then you can use machine learning techniques and that sort of stuff to estimate and get error bounds on nearby ones. And this is good because it encourages exploration of things that you wouldn't necessarily look at. And so, yeah, those would be the two, well, the two ways for the two questions that you had, I think, unless you want further detail.
No, I'm quite happy with the answer.
Okay, thank you.